Hi everybody, I hope you're doing well. Following in this lecture, we will discuss the Bose gas. We already discussed the fermion gas, which fermion particles must obey the Pauli exclusion principle, and therefore they will obey Fermi-Dirac statistics. But now we will discuss a gas of non-interacting or at least weakly interacting bosons, and they must obey Bose-Einstein distribution. Okay, a few important examples of bosons: phonons, photons, and magnons. So in this lecture, we will try to present in a comprehensive manner the origin for the Hamiltonian, the bosonic Hamiltonian in these particular cases. Let us start with phonons. This is the first example. So, vibrations in a lattice or in an atomic lattice. Okay, this problem will produce phonons. Phonons. They are the quanta of the quantum of the lattice vibration. So this is a quantum, a phonon. So phonons, quanta of lattice vibrations. Okay. There are a few important aspects when dealing with phonons. Your lattice can be composed of two or three or many elements, distinct elements, and they will give rise to the emergence of acoustic and optical phonons. The ideas are not too distinct, but in the case of a acoustic versus optical modes, I will discuss in a moment. Okay, so there is a particularities according to the optical or acoustical modes. I will focus here in the discussion of acoustic mode for a single element in the lattice. Okay, but then I will try to bring you a perspective on the optical modes. Okay, and in this case, suppose the following: you have a lattice. I will represent it in one dimension for the sake of simplicity. Okay, you have a lattice of ions. They are positively charged, separated by a distance a, which is the lattice constant. Okay, so this is the, suppose, the x-axis. Okay, in the x-axis you will have one of these ions. So this stands for an ion in the lattice or on lattice. Okay, so this is an ion, and these ions are in equilibrium at a distance a. So this parameter is the so-called lattice constant or lattice parameter. It is the equilibrium distance between the ions in the lattice. Of course, when dealing with the ions forming the lattice, you suppose there is a cloud of negatively charged electrons around it. So there is a cloud of negatively charged electrons. And therefore, if you try to represent the energy here for the interaction between the ions, suppose this is the x1, this is the x2, this is the x3, and it goes on. Okay, it goes on. So for a pair of two lattice points, you could represent the energy in the following way. Okay, this is x. This is the x, some lattice xj, some lattice point xj minus a first neighbor, which is +1 or -1. Okay, it doesn't matter. So I will represent this distance here. Suppose this is equal to some r, some distance between two uh, neighboring sites, and this is the potential energy. Okay, this potential energy can be expanded around the lattice constant because this is the equilibrium position, and it has a very, in a simplistic way, a very well known shape. It is something like this. Okay, so this is the form of the potential energy. Okay, so the minimum is here around A. The distance between the two adjacent points or two neighboring points in the equilibrium at zero temperature is A. And this is the minimum of the energy. This is some U naught here. So it sets the scale of your problem. But if you let temperature enter in the game, these ions will vibrate a little bit, and the system will fluctuate around A in a classical system. But now, remember, we can always expand a potential energy. A potential energy U of R can be expanded around the equilibrium position. So U naught, which is U naught is the equilibrium, U of A, the distance A, plus something like the derivative of the energy with respect to X calculated at the equilibrium position, which is the lattice constant, R minus A, okay, or it is a it is not depending on just on the modulus perhaps, but it's something like this, plus 1/2 the second order derivative with respect to X calculated around this A here, and is the distance, the distance the two neighboring points acquire when vibrating minus the equilibrium squared. And you can go on forever in this series. But since around equilibrium this is 0, you keep this factor here and the Hamiltonian for a classical problem. If you would try to calculate a classical problem, you have a spring here, spring form for potential energy. Of course, this U naught here is some constant. You can drop out from the problem, and you will have a summation over J of the kinetic energies, Pj squared. This index relates to the J plus 1, and so on. Okay, you have a lattice separated in equilibrium by A, but they can vibrate around equilibrium position. And this distance is the equilibrium distance. So you have a pi j divided by twice the mass of the ions. I will use a capital M here just to remember that this mass is, is larger than the electronic mass. Okay, so this kinetic energy is smaller by orders of magnitude when compared to the electron kinetic energy. Okay, but I am trying to focus here on the lattice and the vibration of the ions around the equilibrium points, and plus the spring term, which we could write as a mass omega, which is the frequency of the oscillations, omega naught squared, okay, or just a spring constant here, 1/2, of course, but just to write this in the form of a harmonic oscillator, you will have the following. Okay, you'll have a summation here, summation of xj minus xj minus 1, or you could plug in here a plus and here plus 1 and xj there, it doesn't matter because you are summing over all the j's in the lattice. Okay, so summing over xj plus 1 minus xj plus or minus a. Okay, so if these neighboring points are at the exact equilibrium positions, the spring energy will be zero. But if you just detach this, suppose you fix this one, xj, and you detach the xj plus 1 from the equilibrium, this is A, this is some delta A here, you'll have an energy which has the same form of a mass spring system. Okay, so this is a collection of masses connected by spring interaction, spring-like interactions. Okay, there will be a restoring force if you move one lattice site from the equilibrium. There will be a restoring force trying to bring it back to the original position. Okay, so the problem we want to solve has this form here. It is this Hamiltonian here. Okay, this is the problem to be solved. In quantum mechanics, you need to convert this into an operator corresponding to the lattice sites of your system. Okay, if you have a two-dimensional or three-dimensional system, of course this summation goes for all the neighboring sites. Okay, it will be connected to neighboring sites. Perhaps the potential here depends on some lattice constant A in this direction and some B in this direction and some C in the other direction. Okay, but let us focus on one-dimensional problem for the sake of simplicity. Okay, for the sake of simplicity, because things can be very complicated if you insert more terms there. Of course, you can connect 1/2 of m omega 0 squared to the 1/2 the second order derivative of the lattice potential squared, the second derivative, sorry, calculated at the distance a, and you can just find out what is omega 0. Omega 0 will be squared, will be 1 over the mass, the second derivative of the potential with respect to a. Okay, this will be the mass, the natural frequency of this system. Okay, well, this is just a constant with units of frequency, right? Now you could perhaps just let me rewrite the Hamiltonian here. Hamiltonian will be a summation over J, Pj squared divided by twice the mass, okay, plus m omega naught squared divided by 2 is summation over xj plus 1 minus xj minus a squared. So we could make the following arrangement here, or substitution here. Suppose we have an x of a given position j. This corresponds to j times a if you index the lattice site by distance, by the lattice constant. So you have something like this. This position is 0 in a reference system. This position is a minus a, j a. The next will be j plus 1 times a. And the axis, the position x of the j lattice site will be some j times a, okay? And the j plus 1 will be j plus 1 times a. But now let us introduce a lattice distortion, okay? So plus some small amount psi j, okay? Let me use this letter here, psi j. This psi j is a very tiny displacement, okay? Plus here, plus psi j plus 1, okay? So this is the displacement from equilibrium, okay? This is the displacement from the equilibrium position. And in this term here, remember that P, the momentum P in classical terms corresponds to the mass times the velocity of the j. This will be a vector, but we are using a one-dimensional problem, so this is the component in the x direction. So we will have m, the derivative of the position xj over time. But notice this is just the derivative of this small displacement because this is a constant over time. Okay, so psi j dt. All right, this is oscillating over time, so this is a function of time. Okay, and this is constant in time. All right, this is a function of time. This is a constant in time. All right, so we can use that to rewrite. Notice xj plus 1 minus xj minus a, which is the equilibrium position here, will produce x or j plus 1 times a plus psi j plus 1 as a function of time minus that factor, which is j times a minus psi j as a function of time minus the equilibrium position. Notice that this term here is cancelled by these factors, and we will have xj plus 1 minus xj minus a is equal to psi j plus 1 as a function of time minus psi j as a function of time. Okay, so in this way you have a converted Hamiltonian, which eliminates the A here, because these displacements here are just the variations around the equilibrium position, okay? And therefore, we can rewrite the full Hamiltonian in the following form, okay? This way, we have Hamiltonian is equal to a summation over J. I can write this as mass times the derivative, and in this way we'll have mass divided by 2 time derivative squared, because it is momentum squared here, so it's time derivative squared, plus m omega naught squared divided by 2, okay, summation over j psi j plus 1 minus psi j squared divided by nothing. I put the factor of 2 in front of everything. So this is it. This is the novel form of the Hamiltonian. This is what we need to work right now. Okay. There are other ways to deal with this problem. You can already plug in here a form. So I recommend the following book if you want to go into a little deeper in this problem. And this is by Charles Kittel, The Quantum Theory of Solids. Solids, Chapter 2. Okay, go there and you'll find something like this. You could already convert this into operator. You could just write this as a harmonic oscillator, m omega divided by twice the Planck constant, h bar. And sorry, you could define an aj, which is the following way, is annihilation operator, which is the xj minus I, or plus I, sorry, plus I pj divided by twice the mass. This is operator, this is operator. Of course, you could eliminate that displacement A first, but you have an A dagger J, which is of the following form. You introduce, you can now rewrite M omega. Okay. You could rewrite the X and P using annihilation and creation operators, and in the final step, you introduce a Fourier version of this. Aj is some summation over A of k. This is a spatial frequency or wave number here, because we are just one dimension. If you have more dimensions, it's a vector. Okay, in more dimensions, a vector, but in one dimension, it's just a k, just one number, and ik times xj, which is just a number here. It's just the position of the j ion in the lattice. Okay, it's the jth site of the lattice. Okay, so it's just a Fourier transform. You use this, and you will arrive at the correct Hamiltonian in the end. Okay, but let me follow these steps here. Okay, so take into consideration this Hamiltonian, summation over J, M over 2, d of psi j dt squared plus m omega naught divided by 2, summation over j psi j plus 1 minus psi j squared. Okay. Now let us convert. It is a valid assumption if you consider that your vibrations can be perceived at long wavelengths. So this is a long wavelength approximation. Okay, approximation, long wavelength approximation, and you replace the summation because notice the lattice is composed by ions at specific j's, j plus 1, j plus minus 1, and so on and so forth. So the distance between neighboring points in equilibrium is a. But if you have vibrations which extends with a wavelength of this vibration larger, much larger than the lattice constant, so lambda of the oscillations is much larger than a, you could consider a as infinitesimal. Okay, therefore the lattice constant here is an infinitesimal. Okay, suppose you have a string or a one-dimensional system of length L, the length of the system, the size of your lattice. Okay, you could take this to the limit as L go to infinity, but this is the length L of the system. And in this way, you can replace a summation over J by an integral over dx, and your xj plus 1 and so on and so forth will be replaced by a continuous variable x, and infinitesimal is a. All right, so if you are just calculating something like this, you need to divide by a delta x because you are inserting a summation times a delta x here, which is not present in this form here. So multiply it by delta x, both sides, and divide everything by delta x. The delta x in this case will be the size of the system divided by n lattice points. But this is just the constant, the lattice constant, a. All right, so you need to divide here by a. So in this interpretation is delta x equal to a and infinitesimal. Of course, it is the lattice constant, and therefore you have a mass divided by 2. This function, which is a function of time but is indexed by j, which is a discrete index, becomes a function. So psi j becomes a function of x because psi j is indexing, as a matter of fact, the displacement as a function of time at the side position xj, and this will become a function of position and time. All right, so the total derivative becomes now a partial derivative with respect to time. Okay, And we will have here something like this. Um, let me rewrite here. Okay, so let me rewrite the Hamiltonian. The Hamiltonian will become the following. Will have the following form: an integral over dx m divided by a. Okay, m divided by a partial derivative of psi with respect to time squared. And this is also a summation, so we will have a mass divided by a omega naught here. A summation we already plugged in here. Psi of x plus a, which is our infinitesimal. Okay, let me erase here. Minus psi of x squared. And here we can insert a squared and multiply here by a squared. Because this way, taking the limit a equal to 0, this will become a second order derivative. So plus a squared here, which cancels out one of these a factors. Okay. And the Hamiltonian, this Hamiltonian is converted to a continuous form. Okay. So we will have Hamiltonian in the following form: an integral over dx. This becomes a mass density because notice you have a mass m distributed over a length a, and another exactly equal mass will be in. Okay, so this is minus a over 2, a over 2. This is the length a. You have a mass m. In another point, you'll have another mass m. So m over a corresponds to the mass density of the system. Okay, I'll write it as rho sub m because it's the mass density of your system. Mass density. Okay, mass density. This is squared here. Okay, mass density, mass density. We can just factorize that factor. Mass density times second order derivative with respect to time plus omega naught squared a squared. And if you take the limit of a equal to 0, okay, this is just the following: m psi of x plus a minus psi of x divided by a squared. In the limit a going to 0, this is just the derivative with respect to the variable x. So this is a second order, no, a derivative with respect to x squared. All right. So we started with a discrete Hamiltonian for a lattice points, where we take a long wavelength approximation. Okay, and in this way we could replace the Hamiltonian by a continuous version, and in this continuous version we arrive at the following form of the Hamiltonian. But notice, omega naught is a frequency, is measured in 1 over seconds, and a is a lattice constant. It is measured in meters in the international system. So omega times a, omega times a is just a velocity, a speed. It is the speed of sound, okay? Sound speed. sound speed, right? And our Hamiltonian becomes integral over the x. Of course, you could renormalize the definition of this function here. You could insert the density of mass in the definition of psi, if you would, if you prefer. But let me just continue to write in the mass density here. So this is squared here. Speed of sound squared d psi dx squared. And this here in one dimension, the integral goes from 0 to L or minus L to L, or if you allow your system to be infinite, it goes from minus infinite to infinite, okay? If your system is just an infinite lattice, a one dimension, you will have a Hamiltonian density which depends on x, and of course it could depend on time because there are time derivatives here. And this Hamiltonian density becomes rho m d psi dt squared plus cs squared d psi dx squared. This is the form of the Hamiltonian density. 1/2, I was forgetting this factor, 1/2, 1/2, okay, 1/2, because it has a 1/2 factor here, so 1/2 and 1/2 factor there, okay, so correct, please, this missing 1/2 factor, right? Now you can quantize the psi, the second quantization, okay, second quantization. You write psi of x and t as an operator, okay, it is an operator now, which is a summation over k, okay, summation over k. You could rewrite it as an integral if you want. 1 over a normalization factor, which depends on the value of k, annihilation operator, a plane wave, okay, so this is the plane wave accompanying the annihilation operator plus a dagger, okay, this is a real field, it is chargeless, it doesn't carry electric charge, okay, so this is a Hermitian operator in quantum field, okay, e to the minus I kx minus omega kt. So this is the second quantized version of this field. If you apply some Legendre transformation, you would find the Lagrangian density, which would become this factor of mass divided by 2, time derivative squared minus speed of sound partial derivative squared. You could find this Lagrangian density in the following way. You pick the Hamiltonian, you subtract the Hamiltonian, and you need to just use a canonical momentum times the dot, the time derivative of the field minus h. And the canonical momentum here is just the time derivative of the field times the mass density. Okay, so this is the canonical momentum of your field. If you insert this into this formula, you arrive with the Lagrangian. Okay, we'll have rho of mass, the mass density, times deep psi dt squared minus half. It becomes 1/2, but minus this factor here, which is already here. Okay, but you subtract the Hamiltonian density. And more, if you calculate the Euler-Lagrange equation, you would to calculate the following: deep psi, or the derivative of the Lagrangian with respect to the field, minus the derivative of the Lagrangian with respect to the time derivative of the field psi ddt, minus the x derivative of the Lagrangian with respect to the psi dx. It will be 0, because this is the Euler-Lagrange equation. And you will find out this way. The resulting equation is the wave equation. Okay, so this is the wave equation. Wave equation. Because notice, in the Lagrangian, there is no single term inside. There is no psi term here. And each term is taken to be independent. So psi is independent of deep psi dt, which is independent of deep psi dx. Therefore, you have 0 here, 0 minus time derivative of what? Derivative of the Lagrangian with respect to psi dot. Psi dot, remember, is just the psi dt. Okay? If you calculate the derivative here, you have a factor of 2, which cancels these two. Density of mass deep psi dt. Okay? And now you have ddx, the Lagrangian, the derivative of the Lagrangian with respect to the psi dx. The only term which has the psi dx is this. So we will have a minus cs squared, the mass density. A factor of 2 will come out in front of that, which cancels this, and you'll have deep psi dx, all right, which is equal to 0. Okay, it's equal to 0. The mass density you can drop out of the equation. The derivative of a derivative is a second order derivative with respect to time, with a minus sign here. Minus with this minus becomes a plus. Again, speed of sound is a constant, speed of sound squared, so plus speed of sound squared. Derivative of a derivative is second order derivative with respect to x equal to 0. This is the 1D wave equation. Okay? If you have more spatial dimensions, for more spatial dimensions, you would have here, you would have minus the speed of sound squared deep psi dy minus speed of sound squared deep psi dz squared in more dimensions. So in 3 dimensions, we need to add these terms. And here in the Euler-Lagrange equation, we will have the dy, dl, d deep psi dy minus d dz, dl, d deep psi dz. Okay, with respect to that equal to 0. You just add more factors. Okay, so the Euler-Lagrange equation is just the derivative of the Lagrangian density with respect to the field minus a summation over how many coordinates in the space-time. Let me write this mu d dx mu. Okay, the 0 is time, and the 1, 2, 3 are space coordinates. D of the Lagrangian with respect of the psi x mu. Right? This is the form which is equal to 0. And so you sum over all the coordinates you have. But in one dimension, the result is the following. If you plug in here a psi in a classical term, okay, you are trying to figure out what is the dependence of the wave number or the wave vector k with the omega to find out the dispersion relation. You just remember psi is some psi 0 e to the I kx minus omega t. If you insert this plane wave, this is some a or a here. Okay, let me just write a. In second quantized form, you replace this by a, a annihilation operator. Okay, you replace this by annihilation operator. Of course, the sound wave is a real field, so you need to add a complex conjugate here. So a complex e to the minus tarara, and so on. But if you insert into the wave equation, you'll find out the second order derivative with respect to time is some minus omega squared, which produces omega squared times the psi. This minus is cancelled out. Second order derivative with respect to x produces a minus k squared. So you have minus cs squared, k squared is equal to 0. And therefore you'll find omega of k or k of omega. It depends on what you want to make it as a function of the other. It is a sound speed times k. All right. So this is the function. It's a linear relation. So for the acoustic modes in long wavelengths, which corresponds to small omega, because k is just 2 pi over lambda, okay, you'll have omega of k with respect to k is linear. It is a linear relation. So in the long wavelength, you have a linear dispersion relation. If you properly calculate, not taking this approximation, you'll find out that the phonon dispersion, will have the following behavior. Omega of k is a function of k. It will produce something like this. Okay? And this limit is the so-called Debye frequency. Okay? This is the Debye frequency. If you calculate not in that limit, you don't take the Hamiltonian to a continuous limit because it's based on an assumption which corresponds to long wavelength. The oscillations are represented by a wave with a long wavelength. So for a bunch of nearly displaced sites, for neighboring sites here, the atoms here are nearly in the same phase. So this part of the solid is oscillating towards the positive direction of x. The wavelength is very long. So the reversion, let me write, let me plot here, like this. Okay, so this in this region, I am exaggerating here because this is very small. Okay, in this region here, the lattice ions will be moving to the left, okay, in this to the right. But the wavelength is very long, okay, and therefore a phase which sweeps a region of the material, which is representing the vibration of the lattice ions, the wavelength is larger than the lattice constant. So this, from this 0 to 0, the wave passing through 0, the next node there, this lambda is much larger than A. Okay, this is what I am trying to say. Okay, but if you don't take the continuous limit, you don't consider a continuous problem, you'll find out that the dispersion relation is linear only for small frequencies. At larger frequencies, it will saturate, and the maximum allowed phonon frequency is the dBi frequency. Okay, it is a characteristic of a given material. Well, if you have a lattice composed by two types of ions, suppose like the, the sodium chlorine, okay, so this is an example. You'll have some ions which are plus, some which are minus, okay, some anions and some cations. And in this way, there are modes where both ions are moving in the same direction, in the same sense, okay, in a given region. And of course, farther apart than this region here, you'll have some moving here, but they move together in the same direction, okay? They vibrate, but in the same direction. The plus ions vibrates to the right, the minus also to the right. This is the acoustic mode, okay? But if the plus is moving to the right and the minus to the left, okay, you'll have a optical, because uh, this type of modes here are related to the electric charge, and they will have a distinctive dispersion relation. Perhaps there will be a gap for the smallest wave number. For k equal to 0, suppose the optical mode for k equal to 0, you'll start from some omega here, some omega 1, suppose, and we'll produce something like this. Okay. So the acoustic modes behave like this, but the optical modes, you'll have a gap here. This is a gap because you need, for a lambda going to infinity, which means all the lattice vibrating in the same phase, you need a an energy of the phonon. The minimum is h bar omega 1. So you have a gap, okay, in this case. But I'll not be worried about optical modes. If you make the calculations, if you insert the plane waves, so if you insert the following, a psi operator, which is given by some summation over 1 over the square root of the normalization. this form of the wave as a function of x and t, and you insert this into the Hamiltonian integral over dx, mass density here, the time derivative, you need to calculate the second order derivative here, plus or minus cs squared d psi dx, second order derivative squared. Okay, if you calculate that, you'll find out, no, for the Hamiltonian is a plus here. You'll find out a Hamiltonian which has the important form. We will produce a constant factor, which is vacuum energy. You drop out the vacuum energy, you'll find out something like this. H is equal to summation over k, h bar omega k, a dagger k, a k, which is the number of phonons in the vibrating mode k. So the modes are represented by the dispersion relation, which for long wavelengths assume this form here. Okay, so this k and this omega are interconnected by this dispersion relation here. Okay, but the Hamiltonian, if you plug in here this form into the Hamiltonian, you take the second order derivative, you take the second order, you take the first order derivative and you square that, you take the first order derivative and you square that, you add up, you manipulate your equations, integrate over dx, you'll find out something like this. Okay, this is the form of the Hamiltonian, right? Well, for phonons, that's okay. Talk too much about phonons. I'll let you to do these calculations as an exercise. But the next step, photons. Okay, for photons, they are the quanta of electromagnetic radiation. So I will not give you a full lecture on Hamiltonians and electromagnetic field Lagrangians and all that, because it will demand a little bit more time than I have now. But consider the following: the electromagnetic density, if you remember, electromagnetic density of the electromagnetic field in the international system is given by something like this: 1/2 epsilon of the material, suppose vacuum here for simplicity, the electric field squared, plus 1/2 the magnetic energy. So this is the electromagnetic density. Energy density. So for us, this is the Hamiltonian. Okay, the Hamiltonian density. Is if you are well versed on electromagnetic theory and electric circuits, you'll remember that this corresponds to capacitance times the voltage squared divided by 2, and this factor here corresponds in an electric circuit to inductance, the current squared divided by 2. Okay, so This is if you integrate over a large sample of a material, the fields are homogeneous. Inside, you'll have a capacitance times voltage squared divided by 2. You have inductance squared, the current inductance current squared divided by 2. Okay, so this is the electromagnetic uh, energy density, and in the so-called Coulomb gauge or radiation gauge, I'll not go into that also, but you could write the electric field as a function of a potential vector. Phi, which is the electric potential in your system, is taken to be 0 in the radiation condition, and the divergence of A is taken to be 0. This is the so-called Coulomb gauge. You are just writing the fields in terms of the electromagnetic potentials. So there are electromagnetic potentials, phi and A. In general, the electric field is taken as the gradient of phi, the negative of the gradient, minus the derivative of A with respect to time, and B is taken to be the rotational of the curl operation of A. Okay, you take the curl of A. But now you are just considering phi equal to 0, the divergence of A equal to 0, and E field and B field are calculated in the following way. So if you plug in here, you have the Hamiltonian of your system in terms of this. The Hamiltonian density will be 1/2 the permittivity of vacuum or of the given material time derivative of A, which becomes squared, and the sign just removed because minus squared is a plus 1/2 mu, or if you write it as a magnetic field B, remember B is equal to mu naught times the intensity of the magnetic field H, which is a vector, but I will prefer to use B because H is reserved here for the Hamiltonian. So we will have a 1/2 mu naught will appear in the denominator here. You'll have a curl expression squared for the B. Okay, because this factor here you could write as a B squared divided by mu. So we are replacing the magnetic field intensity by the magnetic flux density B. All right, and a vector squared is to be understood as a dot product of the vector with itself. So this is the dot product of the time derivative of wave with respect to itself. Curl squared is to be understood as a curl times a scalar product with itself. Okay, this is it. So this is the Hamiltonian density. You could, of course, from Maxwell's equations, try to find the equations, the dynamical equations for A. You'll find out from Maxwell's okay. you'll have the following. Divergence of E, we are talking about radiation, is 0. The divergence of B is also 0. You'll have a curl of E is equal to minus dB dt. Rotation, the curl of B is equal to 1 over c squared time derivative of E. Okay, if you replace the magnetic and the electric field in this, which is the Ampere-Maxwell law, okay, if you insert that into that equation, you'll find curl of a curl of A is equal to 1 over c squared time derivative of minus dA dt, because you are inserting the potential, the electric field represented by the magnetic potential vector. So I was forgetting to define it, but this is the potential vector, magnetic potential vector. Okay, magnetic potential vector. This way, there is an identity here which says that the curl of a curl is the gradient of a divergence of that vector field minus the Laplacian of that vector field, which is equal now to minus 1 over c squared, the second order derivative of the vector A with respect to time. And this will lead, because of the Coulomb gauge, 0 here, this will lead to the wave equation, whose solutions are A of R and T are equal to, you need to sum over some amplitudes A of k and the polarization, because this is a vector, so if electromagnetic vector produces polarization, I will write it as epsilon. The epsilon hat alpha is the polarization vector. It can be linear or circular polarization or elliptic, and it can be if linear vertical or horizontal, or if circular left-handed, right-handed. So you have two. So the alpha runs from 1 to 2, or for plus and minus if circular. And k is a vector. K is a vector. E to the I k dot r minus omega t, plus the complex conjugate here, because it's an electromagnetic field, it is a real field, it is not charged. Okay, the photon carries momentum, energy, angular momentum, but doesn't carry electric charge. Okay, so you need to take this as a real field. Complex conjugate here. If circularly polarized light, these circular polarization vectors, they are unit vectors, but they are complex. So this is complex. It depends on the vector k. So it depends on the vector k. Okay, times the exponential, which is the complex conjugate of that, e to the minus I k dot r minus omega t. All right. So this is it for the electromagnetic field. There is a relation which comes from Maxwell's equations. You could insert into the Maxwell's equations and you'll find out that k dot epsilon must be 0. All right, this comes from Maxwell's equations. The electromagnetic radiation moves or propagates in the direction of k, and the polarization vector must be orthogonal. They must be orthogonal. Okay, the electric and the magnetic field are orthogonal to the direction of the propagation. Okay, the wave propagates towards z direction. The electric fields must be in the xy plane. It cannot have a longitudinal component, an axial component. And therefore, these vectors, epsilons, which represent the polarization, which is usually measured as the direction of the electric field. This is electric field because for magnetic field, the magnetic field is perpendicular to the electric, so you don't need to specify twice. If you specify the epsilon, this is the direction of the electric field. Magnetic field will be directed in this direction. So this is for magnetic field. Polarization of the magnetic field is perpendicular to the electric field. So these epsilons here are related to the direction and the polarization of the electric field in the electromagnetic radiation. But it represents the polarization of the wave. And it's the same for A. The electric field and the A polarization vectors are the same. Okay. This way, you need to ensure this fact here because the direction, the wave vector contains is in the direction of propagation of that wave, and of course the electric field must be perpendicular to that direction for a plane wave. Okay, so expand the field, expand in terms of plane waves. Of course, if you insert into the Hamiltonian, you need to calculate, well, first you need to second quantize, therefore second quantization. Let me erase here. What is the procedure? Second quantization. You need to replace the A by some annihilation operator with some numerical normalization factor. You can find out what is this normalization factor, but it's something like 1 over square root. And I guess we have something like this. H bar divided by twice the frequency, the volume, the epsilon naught, the epsilon zero of the vacuum. Okay. Remember also that the speed of light is 1 over the square root of this product here, this speed of light. And this is the volume. So the normalization depends on the omega. And you just use a set of harmonic oscillator, a collection of harmonic oscillator to represent the electromagnetic field. Okay. The A dagger, the conjugate A is replaced by the dagger. So the same normalization factor because it's a real number times A dagger of K and alpha. And then after you replace this into that, you have an operator a vector operator A. And this way you can now plug in into the Hamiltonian, which is a integral over the volume of the Hamiltonian density from minus infinity to infinity in all directions. So it's a volume integral over the entire volume of space, 1 over 2 epsilon naught, okay, epsilon naught, time derivative of A squared. This is a vector product you need to take into account. Another important relation is that epsilon times the conjugated epsilon beta is equal to delta alpha beta. Okay, so the only way you get 1 is for the same alpha and beta, and normalize it to 1. So if you insert that into the Hamiltonian, you'll have 1/2 of this factor, which comes from the electric field, plus this factor here, which comes from the magnetic field. Okay, you'll have to deal with a little bit of algebra, vector algebra, but if you do the math, in the end, you'll find out the following Hamiltonian. In the end, summation h bar omega of k, it doesn't depend on the polarization. Usually, you need sum over all the k's, all the alphas, the number operator for photons. Okay, the idea is that, okay, you start from the electromagnetic energy density, which is the Hamiltonian density for the electromagnetic radiation. You can consider a particular gauge, in this case, the radiation gauge condition or the Coulomb gauge, for which the divergence of this vector is 0. Okay, the divergence being 0 will produce for you that condition k dot epsilon alpha equal to 0. Okay, this will produce that condition, which is the transversality of the electromagnetic waves. And then, after you expand the vector A in terms of plane waves, which we already know it satisfies the wave equation, the dynamics of this field must satisfy the wave equation. We already know that. You plug in into the wave equation, you'll find out that omega is the speed of light, or the light speed times the modulus of the vector k, which we just write as k, right? This is the dispersion relation for light or for electromagnetic waves. If another material, not the vacuum, this is the speed of light in that material, in that medium, right? So with the Hamiltonian density in your hands, you just expand the vector A in terms of plane waves, replace the amplitudes of the normal modes, these are called the normal modes, replace them by annihilation and creation operator, and with a proper normalization, you will arrive with this form here. H bar omega k, the number operator, which corresponds to A dagger A. Okay, plus vacuum energy. Okay, plus the vacuum energy. But the vacuum energy is not it cannot be directly measured. There are an effect which comes from the vacuum energy, which is called the Casimir effect. So if you are interested in the subject vacuum energy has the following form. Summation 1/2 h bar omega k over all the alphas, and this diverge. It goes to infinity. So you remove this infinity because you have an infinite set of harmonic oscillators with this energy. So remember, for a single harmonic oscillator, you have omega, h bar omega times the number of particles in that state plus 1/2. So the summation over n is this factor here, and the summation over this 1/2 produces a constant, but k is summed over from 0 to infinity because you have all directions of space. If you take the limit to the continuum, this will diverge, or even in the discrete set, it will produce a discrete but infinite set. The summation of this part here produces an infinite. Okay, but if you have a infinite which is discrete and an infinite which comes from a summation over a continuum, the values of the infinites, it's weird to hear that, but they are different. This is called the cardinality, and this produces an effect which is called the vacuum force. If you have two metallic and perfectly parallel plates, the vacuum inside the plates produces discrete modes of vibration, and this way the vacuum is a summation over discrete modes. But outside you have a continuum, and the continuum will produce a force tending to move one plate towards the other. This is called the Casimir force and Casimir effect. Casimir effect. So if you are interested in that fact, just take a look, Google it, find out what is the Casimir effect. But for us, the vacuum energy is just a reference level, so we are just sweeping out, okay, an infinite energy. But it doesn't matter because the physically measurable or you can observe are the photons, and it is this part here. Okay, so for photons you have the same form of the Hamiltonian. So notice it is becoming repetitive because the form of the Hamiltonian for phonons. Hamiltonian corresponds to summation over k, h bar omega depending on k, number operator. But in one dimension, phonons don't have any polarization effects. Okay, so there is no need for polarization term here. For photons, summation h bar omega, but now you will need to add a factor of 2 because there are two possible allowed polarization for light. The total number of photons in the form of the Hamiltonian is the same. This operator is not that, okay? So this is the annihilation creation for photons. This is for phonons, okay? But if you have photons and phonons in your problem, perhaps it's better to use another symbol here, a B or another symbol, okay? Some another symbol for phonons, okay? You could guess what is for magnons. For magnons, okay? There are ferromagnetic magnons and antiferromagnetic. It depends on the type of the material. Okay, but the starting point is the Heisenberg Hamiltonian spin Hamiltonian. It has the following form: minus some constant, which is called the exchange integral. It depends on the exchange of identical particles, and the summation over spins. Okay, it can be a vector operator for the spin in the lattice point I, dot product or scalar product with spins in the site J. There are more complicated spin Hamiltonians, okay, but the analysis is more complicated, but in the end you can find out Magnonic modes. Okay, you sum over I and J neighbors, first neighbors, but it can be in more than one dimension, of course. So you need to sum over all the J's which are first neighbors to I for all the I's. And you can use some proper ordering for the summation. So usually is symbolized by these brackets here. You just need to order the summation, just not to count twice. But if you don't want to count, put order here, you sum for I and then you sum for J the same energy, you divide it by 2 here. Okay, you could divide this by a factor of 2. And of course, there is spin interactions with external magnetic fields if present in the system. So you have a constant, suppose a magnetic dipole moment, a magneton or some constant here, I will call it nu, okay, summation over S at the site I times the magnetic field experienced by that spin at the site I, summed over all the I sites. Right? If the system is ferromagnetic, this term is what ensures you have a ferromagnetism. You don't need to have a magnetic field to have a magnetization. Notice that if you think classically, these are quantum operators, but if classically, you could think that the most favorable scenario is that for a spin to have a parallel alignment with its neighbors. Why is that? Because this minus sign here favors the alignment. You have a lower energy if the spins are aligned. Okay, so spins are aligned in the material. Of course, if you have a plus here, you have anti-ferromagnetism. Or if J is positive, for J positive, suppose J higher than 0, greater than 0. If you have a negative number, you will have an anti-parallelism. It is favored. So this is ferromagnetism. This is anti-ferromagnetism. Okay, in very simple terms, there are materials pertaining to this magnetic order, and there are other materials pertaining to this ferromagnetic order. But let us concentrate on ferromagnetism. Okay, you could just you could just insert an impulse into this spin and allow it to fluctuate. So if you have a magnet, you kick it and it fluctuates. Okay, there are neighbors, they will start to fluctuate also. Okay, so if you fluctuate this will fluctuate, this will fluctuate, and the other will fluctuate. and you'll have some form of wave here. Okay, if you kick one of the spins in the lattice, suppose the lattice is this thing here, you just insert a little bit of thermal energy perhaps into this will oscillate, and it will transfer the oscillation to the neighboring sites because they try to align again. Okay, and therefore you will have a wave propagating throughout the material, the spin lattice. Okay, this is a very simple model because this is for localized spins. There are also the so-called itinerant magnetism, which comes from indirect interactions. The ions have spins. They transfer some information to the conduction electrons, and these electrons polarize and transfer the information to other sides of the lattice. Okay, but suppose for the sake of simplicity, you have a lattice of spins, and these spins, the lowest energy level is it's proportional to the alignment of all the spins. Okay, and if you just kick one of them, it will jiggle a little bit, it will transfer the fluctuation to its neighbors, it will produce waves. These are called spin waves. You can use, of course, the Heisenberg equations of motion to find out using the angular momentum algebra what is the equations of motions for the spins, and you can solve it almost classically. Okay, but if you want to quantize these spin waves, the quanta of spin waves are called magnons. Okay, these are the so-called magnons, and magnons have a quadratic dispersion relation for ferromagnetic magnons. Okay, so for ferromagnetic magnons, omega of k is some constant. Let me call it a times k squared. Okay, it's a parabolic dispersion relation. In contrast to phonons in the long wavelength, which corresponds to this dispersion relation, to the case of photons, it is the same of phonons with the replacement of the speed of sound by the speed of light. Here you have a distinct form. Okay, but I recommend here for this part, chapter 4, Quantum Theory of Solids by Kittel. Okay, Quantum Theory of Solids by Kittel, Charles Kittel, and there you'll find out the steps towards finding out the Hamiltonian of this ferromagnetic system. What you'll find out is some constant energy which is somewhat proportional to n times the spins squared. Okay, the spins squared, you'll find out that factor, and also you'll find out a part which corresponds to magnons, and magnons tends to introduce a disorder into the magnetization. Okay, so the energy of this state, the Hamiltonian, will become the energy of the fundamental state, which corresponds to the alignment of all the spins. Okay, And this is negative energy because for ferromagnetic, so ferromagnetic magnons, you have the following form, okay? Minus some fundamental state energy plus the energy introduced, which is positive, because the most favorable state is this fluctuations tends to enhance or increase the energy of the system, plus the Magnon system energy. Usually we have, I'll use B for the annihilation and creation operators, and for Magnons, omega and K in the long wavelength satisfy quadratic dispersion relation. If you insert a magnetic field, it will insert something here which is it corresponds to a gap. Okay, if you insert magnetic field, it enforces even more the magnetization of your system in the direction of the magnetic field. And for you to kick one of the spins and make it oscillate, it will need more energy. And the quanta will appear to have a gap. And this gap is related to the amplitude of the applied external magnetic field. But if no magnetic fields, external magnetic fields, the system magnetizes spontaneously, producing the ferromagnetic order, and thermal fluctuations, so magnons here, you will produce thermal fluctuations. They have a quadratic or parabolic dispersion relation. Okay, this is it for magnons. To get there, you start here, Heisenberg Hamiltonian, and you use something called Holstein Primakov transformations. Okay, Holstein Primakov transformations just replace the spin ladder operators at sites. Okay, S plus, which adds one spin, S minus, which lowers the spin by one unity, and SZ, which measures the state of spin in that site. They are replaced by something which is, this is the is proportional. Okay, the S plus is proportional to the annihilation of a magnon, because if you annihilate one spin wave, you are increasing the spin of the lattice. S minus, which corresponds to the creation of a magnon, and Sz, which corresponds to n times the spin of one of the lattice points, and n is the number of lattice points. This S doesn't need to be half. In general, you could have a total spin of a ion in the lattice to be 8, 6, 10, whatever. Okay, so n lattice points times S minus something which is related to the total number of magnons. So B dagger B. Okay, summed over 1 over n, summed over all the factors of K. This is the total Magnon number. Okay, I don't quite remember if this 1 over n is present in the definition or not. No, I guess not. So you don't have to plug in anything else. It's just what is the total spin of your system. It is the total number of up spins. Suppose they are aligned in the up direction. It could be down spins, but in general, suppose alignment in the up direction. The direction of alignment, suppose this is the positive direction of the z-axis. Okay, this is the positive direction. So you'll have 1, 2, 3, 4, 5, n times the maximum allowed projection of the spins, okay, which is s, n times s, minus what the spin waves do to make the system out of the most favorable state at temperature equal to at absolute zero. Okay, so I'm finishing here. In next lecture I will try to discuss the photon gas and the black body radiation. I guess this lecture could be useful. I know I discussed three topics, very complicated issues in a single lecture. Okay, but the literature is vast. There are a lot of examples out there, and I know you can find out more on these subjects. Okay, so here what I'm trying to really to point out is the fact that in second quantization, a free particle gas, a non-interacting gas, or weakly interacting to the lowest order approximation, it can always be written in the number representation. Okay, it's the energy of a given quantum times the number that of that type of particle. It applies for bosons and for fermions. Okay, the only difference is the dispersion relation between the frequencies and the wave numbers. In this case is parabolic, in other cases linear, in another still another more complicated case is another formulation. It's just a relation of omega depending on k, on the wave number. Okay, so this is the energy of the particle times the number of the particles. What changes? The dispersion relation and the algebra. For bosons, these operators, annihilation and creation operators, satisfy bosonic algebras. For fermions, which we already discussed in the fermion gas problem, fermionic algebra. But apart from that, non-interacting or weakly interacting problems will be described to the lowest order by something like this. Okay? By a Hamiltonian in the number representation whose eigenstates are number states. Okay? Bye bye. See you next time.